Now I will talk about magnetic circuit analysis, which is an approximate technique to calculate the magnetic field that would appear between the poles of an electromagnet. So you can think of a closed magnetic circuit as a toroid and an open magnetic circuit as one that has free poles, north and south poles, that were introduced by producing a gap at some location in the inside the toroid. Okay, so the analogy with the electrical circuits goes as follows. So if you think about a battery that is connected to a resistor, in this very simple circuit, uh, this is the voltage provided by the battery and this is the resistance of the resistor, and you know that the voltage is going to be equal to the sum of the current multiplied by resistances in the circuit. So if you have other resistors as well, it will be the same current that flows through the circuit, and you would see Ohm's law basically. So this is Ohm's law for electrical circuits. And what is the voltage that appears between points A and B? It is minus the integral from B to A, the dot product of the electric field with the dl vector, which is a vector that points in the direction of the current. So E dot dl. The analogy in the magnetic case is that we define a magnetomotive force, motive force. So this is the analogy to voltage, Vm, and this magnetomotive force is given by sum of the flux multiplied by what is known as reluctance of the circuit. Okay, so in this analogy, the flux is analogous to current, the reluctance is analogous to the resistance of the circuit. And if you write Ampere's law, for example, for this closed loop, you can see that the closed loop integral h dot dl, Ampere's law, I'm writing this in SI units, this is equal to number of turns n multiplied by the current I that flows in the circuit. So n is number of turns, and I consider the current that flows between these is I. So there's a winding with n turns, and we have the total magnetomotive force Vm is equal to the number of turns multiplied by current. Well, this is just Ampere's law. Basically, the closed path integral h dot dl is equal to the total current enclosed, which is n times I. Okay, so well, H and B are related, so we can write H as B divided by mu. So B is equal to mu H. Permeability times the magnetic field is the magnetic induction B. And the total length, the length of the path, so here L would be equal to, if you consider the radius vector R here, L would be equal to 2 pi R. So B over mu multiplied by the total path length L, path length, L must be equal to n times I. So if I multiply the top and bottom with area, so if I multiply this with area and divide it by area, what would I obtain? I would obtain the flux. So flux multiplied by L over permeability times area A is equal to the magnetomotive force, which is N times I. So we find that the reluctance Rm is equal to L divided by permeability times area A. So A is area. So this would be basically the area that is cross-sectional area. Okay, so reluctance is the total path length L, which would be 2 pi r in this case, divided by mu times area A. So here the reluctance would be 2 pi r divided by mu times area A. Okay, now we have found what the corresponding value of resistance in magnetic circuits is. That's called reluctance. So you can take this analogy further and you can come up with a set of names that forms this analogy. So the first thing we see is that current, which is the electromotive force divided by the resistance, that's Ohm's law, is analogous to flux, and that is magnetomotive force divided by reluctance. And current is denoted by I, flux is denoted by phi. Electromotive force is usually shown with epsilon here, not E. So this is usually shown with epsilon, is analogous to magnetomotive force, which is N times I in SI, the number of turns times the current in SI, or 4 pi over 10 N times I in CGS. Well, you can show this if you wish. The resistance, which is rho L over A in electrical circuits, or L over sigma A, is reluctance L over mu A, mu R times A in SI units, the relative permeability times A, or L over mu A in CGS units. The resistivity rho is analogous to reluctivity, which is 1 over mu R. Conductance is 1 over R. Its permeance, which is mu times area, mu R times area divided by L. And conductivity sigma is permeability mu R in SI, or mu in CGS. Okay, so let's see if we can find this analogy for the magnetomotive force. As we said, the total magnetomotive force is total current enclosed by the loop, which is N times I. So that's in SI. So if I were to do this in CGS, remember that the H value in CGS is basically H is equal to P divided by R square in CGS, and it is mu 0 over 4 pi P. It's not mu 0 is not here, so 1 over 4 pi P over R square in SI. and B is equal to mu 0 h in free space, right? So if you go back to Ampere's law, so Ampere's law written in CGS and SI, if you remember, Ampere's law in CGS is equal to 4 pi times current enclosed, so this would be equal to 4 pi Ni, and therefore you would find that if the current is given in ab amps, so this is in CGS EMU, current in ab amps, you would find that the magnetomotive force Vm should be given as 4 pi Ni. But if the current is given in amps instead of ab amps, so this is CGS EMU, it could also be written as 4 pi over 10 Ni, which is CGS mixed units, so where you would have the current in amps. So we can check this. If you remember, 1 amp, 1 ab amp is equal to 10 amps. So if you have the 1 ab amp, you would get 4 pi n times 4 pi n as the answer. If you have if you put here 10 amps, you would also get 4 pi n for the magnetomotive force. So that's one way to check it. So here we say CGS, it's actually CGS mixed units, so because the current is given in amps here. So as you can see, we have to be very careful about units in making these conversions. Okay, so now let's talk about an example. How can we use this information for an actual magnetic circuit? So here we have a toroid that has 400 turns. The radius inside is 2 centimeters, outside is 3 centimeters. The question is, what is H if current is equal to 1 amp? What is the flux density if the toroid is filled with air? What is the flux density if it's filled with iron? And what is the flux density in an air gap 1 centimeter in length? Okay, so let's see. For part A of the problem, I'm going to write the magnetomotive force. The magnetomotive force, Vm, is equal to N times I in SI. So that's basically found by forming a closed path here. That's an Amperian loop where we see the total current enclosed by this path is equal to N times I. This is the closed path integral H dot dl, which gives for us, because we have the same magnetic field that is circulating around, and H and dl vectors are parallel to each other inside the toroid, we would have H times 2 pi r bar, where r bar is r1 plus r2 over 2. So that is corresponding to the circumference of this circle, which has a radius now r bar, the average radius. So this is basically 2.5 centimeters. Now, since I'm using SI units here, I'm going to convert this to meters. So 2.5 times 10 to minus 2 meters. So then I can calculate H times 2 pi r bar is equal to Ni. So I find that H must be equal to Ni divided by 2 pi r bar. So N times I, for a current of 1 amperes, it's going to be 400 amperes divided by 2 pi r bar, which is 5 pi 10 to minus 2 meters. This is approximately equal to 400 so you would have the 10 to minus 2 upstairs, so we can easily calculate this. It would be 40,000 divided by 5 divided by pi. That would give us approximately 2500 ampere per meter. It's just, well, this whole thing is an approximation anyway, so this is giving us a value that is somewhat close to the actual value. Now, in part B, what is the flux density B if it's filled with air with relative permeability that's equal to 1? Well, in SI, the relationship between B and H is B is equal to mu 0 H. It's actually mu 0 H plus M, but with air, M is equal to 0, so it's equal to mu 0 H. So we would find 4 pi 10 to minus 7 Henry per meter multiplied by 2500. This gives us a B value inside as 3.1 millitesla. So Tesla is the unit in SI. Now in part C, what is the flux density if it's filled with iron? Now the relationship between B and H is B is equal to mu H, which is relative permeability mu 0 times H, and this would give us mu r times the B value that we have calculated here. So this would give us 100, which is the relative permeability, times 3.1 millitesla, which would give us 310 millitesla. So 100 times higher magnetic induction inside. And for part D, so let's do that here. What is the flux density in an air gap? Okay, so if I put an air gap, the magnetomotive force I have to rethink. So let me open up some space here. So in part D, the reluctance has changed. So the magnetomotive force is equal to the same flux that flows through the circuit times the reluctances. So this would give me, this equation would give me 400 times 1 amperes is the flux in the iron, length of the iron, divided by mu of the iron times area of the iron, plus flux in the air part, length of the air part, divided by mu of air and area of the air part. Okay, so flux is continuous, or we're assuming that it is approximately continuous, because we have leakage that we are not taking into account. I will get back to this in the remarks. So flux is approximately continuous, so we're saying that the flux in the iron should be the same thing as the flux in the air, which I will call phi, and the area in the iron component and air components are the same, so it's area A. So basically we have opened up some space here in the toroid, and now we have basically this configuration with the gap opened inside. So this part has the same cross-sectional area. A is the same. The length of the iron part, this is the length of the air part, and then we have different mu values for different regions. Okay, so we can write our Ohm's law for magnetic circuits. Magnetomotive force is flux divided by mu 0 A times length of the iron divided by mu r plus length of the air divided by mu r for iron and mu r for air. So this is going to be the Ohm's law, and B times A is our flux phi. So Ni is equal to B over mu 0, because I have the areas cancelling, B over mu 0, multiplied by length of iron divided by relative permeability of iron plus length of the air part divided by 1, because that's the relative permeability for air. So we find that the flux density B, or magnetic induction B, must be equal to mu 0 Ni divided by length of iron part divided by relative permeability of iron part plus length of the air part divided by 1. So this gives us 4 pi 10 to minus 7 400 amps divided by length of the iron part. So length of the iron part we have to calculate. The air gap has 1 centimeter length. The total length was calculated as 5 pi 10 to minus 2. So what is the total length here? So the total length 2 pi r bar was 5 pi 10 to minus 2 meters, which is approximately 15 10 to minus 2 meters. So I'm taking pi to be 3. So this is going to give me 0.15 minus 0.01, which is the length of the air part, divided by relative permeability of iron plus 0.01 divided by 1. So at the end I find the flux density in the gap to be 0.044 Tesla, or 44 milli Tesla approximately. So I see that no gap was 310 millitesla. With gap I have 44 millitesla. So there is a substantial decrease in the flux density by introducing a gap in between the two poles here that we are forming. Okay, now I have a few remarks about this calculation. The first one is if we have a very high permeability material, for very high permeability materials, we find that the gap dominates the response. And why is that? Well, you can think of the reluctance, if you go back to our reluctance, which is L divided by mu A, if you have a very high permeability material, the reluctance for that part of the magnetic circuit goes to 0, so it behaves as if it's a short circuit, but the air will have a substantial reluctance, so it will dominate the response. If you look at B versus I curve for a magnetic circuit, B versus I, if we have no gap, we're going to have this type of behavior, and if we have a gap, we're going to have this type of behavior. So that is with gap. And that has to do with the change in the permeability. As you can see, so from this plot that I have here, there is no hysteretic behavior. When I change the current, I'm increasing the magnetic induction linearly. So there is basically an approximation here. So number 3, there is a flux leakage in the gap that we are not considering. So how does that work? If you have a gap in an electromagnet like this, and if you look at the field lines point from one pole to the other, but then you will have these field lines which will be leaking out from the ends, so you will have flux leakage. And number 4, when we are making this analogy, you have an electrical insulator, but there is no magnetic insulator. Even if you have air that is not insulating to a magnetic flux, so there is no magnetic insulator. The closest you can get is superconductors. So superconductors, due to Meissner effect, are acting as perfect diamagnets, so they can be acting as a magnetic insulator up to a certain field, but not perfect magnetic insulators either. And number 5, hysteresis. Hysteretic effects are ignored. Hysteresis ignored. Only initial magnetization curve considered. So if you remember, we have in ferromagnetic materials hysteretic behavior, so B is equal to mu H doesn't really apply if you don't have a linear relationship between B and H, and the magnetization basically changes, or B changes with H in a non-trivial manner. Okay, so let's summarize what we said. Well, we find that if you consider an electrical circuit where we have Ohm's law, the electromotive force V is equal to sum of the currents and resistances in the circuit, where the voltage between 2 points A and B, VA minus VB, is equal to minus the integral B to A E dot dl, electric field times the dl vector. Magnetomotive force, on the other hand, is sum of flux times reluctance, and reluctance is analogous to resistance, flux is analogous to electrical current. If you write Ampere's law for a closed path H dot dl is equal to Ni, using SI units, that integral h dot dl is your magnetomotive force. So N times I is the magnetomotive force. That's the total current enclosed. And for H, you can write B divided by mu. So once again, we're assuming initial magnetization curve. So B divided by mu, H times L is equal to Ni. So if you multiply top and bottom with area, you have flux inside the material, B times A times L over mu A. L over mu A is reluctance. And you can see this analogy here. Current is flux, electromotive force is magnetomotive force, which is Ni in SI. Resistance is rho L over A, reluctance is L over mu A. Resistivity is rho, reluctivity is 1 over mu. Conductance is 1 over R. Permeance is mu A over L. And conductivity, sigma, is analogous to permeability, mu. And here I have done some small calculation in order to check this magnetomotive force. Just for CGS mixed units, we find that magnetomotive force is 4 pi Ni over 10. It's not Ni as in SI units. So we have to be careful with these unit conversions. Now we have gone through an example where we have a toroid with N turns, 400 turns, inner radius 4 cm, outer radius 3 cm, with 1 ampere current, writing the magnetomotive force N times I is equal to H times 2 pi R bar. We can calculate the magnetic field inside, 2500 amps per meter. If it's filled with air, if there is no material in the toroid, then it's B is equal to mu 0 H, and you would have a B of multiplying the H by mu 0, 3.1 millitesla. If you have iron, you have mu H or mu 0 H plus M. So this is the same thing as mu 0 H plus M. And mu is equal to mu R times mu 0 H. So it is 310 millitesla. If I introduce an air gap, then I have a reluctance that is due to the iron part and air part. The reluctance due to the iron part is length of the iron part divided by mu iron area iron. Reluctance of the air part is length of air divided by mu air area air. The flux is assumed to be continuous. The area is the same. There is no change in the cross-sectional area. Even though I haven't drawn this perfectly here, we're assuming that we have the same cross-sectional area here and here. It's the same area. And the total magnetomotive force Ni will be phi over mu 0 A, length of iron divided by mu R of iron plus length of air divided by mu R of air, and we can calculate B to be 44 millitesla here. So we find that with no gap we have 310 millitesla, with gap we have 44 millitesla, and if we have just air, we would have 3.1 millitesla. So you can see the difference depending on what material the toroid interior is filled with.